We ended last time talking about different forms of matter and how pure substances that cannot be broken down chemically or physically, we call them elements. So an element, again, is just any substance that cannot be broken down chemically. And each element has unique properties that are associated with that element. Like, for example, this is gold right here, and gold has unique properties of being a metal, certain melting point. This is iron, right? This is mercury, right? They all have, each element has its own unique properties and is composed of atoms, but only of atoms of that specific element type. Here, we're going to dive more into what atoms are and atomic composition. Again, atoms are the building blocks of elements. Atoms are the building blocks of molecules as well, right? Each atom of every single element is composed of what we call subatomic particles, and it's these different subatomic particles that give elements their unique characteristics. So this is a very simplistic diagram. This is not actually what atoms look like, but we can see, based on this representation of an atom, in the middle here we have what's called the nucleus. This is where we find the subatomic particles called neutrons and protons. And then orbiting around the nucleus, we find the subatomic particles, electrons. But how big is an atom relatively? It's kind of something very, very hard to conceptualize. So for example, if we were to take just one sheet of normal paper, like a sheet of printer paper or something, how many atoms would it take for to stack them up on top of each other? How many atoms would it take until we got to the thickness of that one sheet of paper? We would have to take about 1 million atoms stacked together to reach the thickness of one sheet of paper. 1 million atoms to reach the thickness of one sheet of paper. So these are incredibly small. But let's dive more into the different components of the atom and how they function. So starting in the nucleus, let's start talking first about the protons. So the number of protons in the nucleus gives us what's called the atomic number. So in the periodic table, you'll see this kind of notation where we have the atomic symbol, like C for carbon, and you get the mass number and the atomic number. The atomic number is always the number of protons that are in the atom. Protons have a charge of +1, and we say they have a mass of 1 atomic mass unit. AMU is an arbitrary mass that we gave to these subatomic particles. So these number of protons, this is what gives the atom its characteristics, its identity. If we were to change these number of protons, let's say 7, this would no longer be carbon. It would then be nitrogen. It would be a completely different element if we change the number of protons with a completely different set of characteristics. Protons +1, mass of 1 AMU, and they're found in the nucleus. The other subatomic particle found in the nucleus is what we call the neutrons. Neutrons have 0 charge, hence the name neutron, they're neutral. They also have a mass of 1 atomic mass unit, and it's the number of neutrons and protons that gives us the atomic mass for that atom. So most, around 99% of carbon atoms are carbon-12. So they would have an atomic mass of 12, meaning that in their nucleus, they have 6 protons and 6 neutrons. So they have a mass of 12 AMU for most carbon atoms. But we can change the number of neutrons in the nucleus without changing what element the atom is. So the majority of carbon atoms will be carbon-12 with 6 protons and 6 neutrons. About 1% of the carbon atoms on Earth are what we call carbon-13. Carbon atom that has a mass of 13, because it has an extra neutron, it has 7 neutrons instead of the typical 6 that we find in carbon-12. But it's still carbon. It reacts chemically the same way, and it bonds similarly the same way as carbon-12 does. Same thing with carbon-14. Carbon-14 is still carbon, but now we have 6 protons and 8 neutrons. Carbon-14 is not as common. It's a very, very relatively rare isotope of carbon, but it still behaves the same way as carbon-13 and carbon-12. So if an atom has the same number of protons in its nucleus, but a different number of neutrons, like carbon-13 or carbon-14, we call those isotopes. Some isotopes, like carbon-14, will go through radioactive decay to attain a more stable configuration. So for instance, carbon-14 is an isotope of carbon that is formed high in the atmosphere when nitrogen-14 is hit with a cosmic ray and a free-floating neutron. Cosmic rays are constantly bombarding the atmosphere, breaking apart these atoms, and so it's not uncommon to just have free-floating neutrons run into another atom. When this happens, this adds a neutron to this nucleus, but then causes this new atom to eject a proton. So we add in a neutron, but eject a proton. So we're going to decrease the atomic number by 1, but the mass stays the same. So that's how carbon-14 is formed, and this is a constant process. This is a continuous process. So the amount of carbon-14 in the atmosphere is relatively stable throughout time. So living organisms have a relatively stable level of carbon-14 in their tissues. Since plants uptake carbon dioxide from the atmosphere, some small amount of carbon dioxide that they will uptake will be in the form of carbon-14. While most of it's going to be in the form of carbon-12, we will see some carbon-14 in the tissues of plants because they're uptaking the carbon-14 from the atmosphere. That carbon-14 will then get integrated into the tissues of the plant through the process of photosynthesis. And it can also be transferred to any animals that eat the plant. So animals that eat plants that are using carbon-14 will also have a relatively stable level of carbon-14 in their tissues. However, once an organism dies, its levels of carbon-14 will no longer match that of the atmosphere because that's no longer uptaking carbon from the atmosphere. And after around 5,730 years, the amount of carbon-14 in the tissues of a dead organism will be about half of that of an organism that's alive today. So let's say we find a wooden spoon in an archaeological site. We can, using what's called mass spectrometry, test that wooden spoon to determine how much carbon-14 is in that spoon. And that can tell us if it's 50% or 25% of the carbon-14 that's in the atmosphere today, how long ago that spoon was made. So what's happening in this decay, what we call radioactive decay, is that carbon-14 is going through what we call beta decay, in which it ejects an electron from its nucleus. This is kind of the tricky, weird thing about radioactive decay. If we think about each of these neutrons, the neutrons themselves are basically a proton and an electron combined into one neutron particle. And so what happens is that basically one of these neutrons is converted to a proton, and then that electron is ejected from the nucleus. So we are going to basically reverse this process and convert one of those neutrons back to a proton, where the mass will stay the same, but we will increase the atomic number back up to 7, so it becomes, again, nitrogen. So the net effect of this beta decay is that a neutron is converted to a proton. So the overall mass number remains the same, but the number of protons increases by 1, and the atomic number goes up by 1. So carbon-14 is converted into nitrogen-14. The third atomic particle are the electrons. So electrons essentially are massless. We say they have a mass of 0. So their mass is so infinitesimally small, we don't even say that they have a mass at all. So for our purposes, we'll say electrons have a mass of 0. They have a charge, electrons have a charge of -1. So in an atom that is electrically neutral, if it has an overall charge of 0, the number of electrons and the number of protons will be the same. So if carbon, for example, has 6 protons, if it has an overall charge of 0 to that carbon atom, it will also have 6 electrons. So we'll sometimes show atoms with electrons moving in distinct orbital spheres. That's a simplistic diagram that helps to represent the behavior of electrons, but electrons are really just orbiting around this nucleus in a random fashion. And what we're looking at here with this diagram is the probability that we find an electron orbiting around this helium nucleus. The darker the color as we move into the nucleus, the more likely we are to find an electron in that area. So there's a large space, three-dimensional cloud, orbital cloud, in which electrons could be moving around the nucleus, but we're just most likely to find them close to the nucleus. So the diagrams that we'll be looking at are simplified versions of this idea. They just help to crystallize the idea of electrons and where we can find electrons. We will talk more about electrons later when we talk about chemical bonding, because chemical bonding is really talking about the interaction of electrons between atoms. So just like we can alter the number of neutrons in an atom, we can also alter the number of electrons that are present in an atom. Some atoms might readily change the number of electrons. Some atoms are more stable and their electron number doesn't change. But regardless, if there's a different number of electrons than there are protons in an atom, that's going to give that atom a charge. So here we have a carbon atom that has 6 protons and 6 neutrons, and it has 6 electrons. So these 6 protons with a +1 charge balance out these 6 electrons with that negative charge. But now let's say we have an atom that has only 5 protons, but it has 6 electrons. Because we have 1 more electron than we do protons, the overall charge to this atom is -1. So we would say that this is an ion. Specifically, we would say this is an anion. An atom that has a negative charge due to a difference in the number of protons and electrons is an anion. In this atom over here, we have 6 protons, but only 5 electrons. So now we have 1 more positive charge than we do negative charge. So the overall charge to this atom will be +1, so it has a +1 charge. In any ion, any charged atom that has a positive charge, we call it a cation. Atoms may gain or lose electrons based on a few factors, which we'll cover later, but they can exchange electrons. That exchange of electrons results in a different number of protons versus electrons that will give that atom a charge. All right, quick review of the parts of an atom. Neutrons are in the nucleus, 0 charge, 1 atomic mass unit, and they're really there to kind of hold the nucleus together. Protons are also in the nucleus. They have a +1 charge. They also have a 1 atomic mass unit for their mass. And they give the atom its characteristics. They tell us which element that atom is. Electrons have a -1 charge. They're essentially massless. They're found in orbitals zooming around that nucleus. And they tell us the reactivity of an atom, how likely and what types of reactions that atom will go through. And remember, what happens if we change different parts of this atom? If we change the number of protons in the nucleus, that gives us a totally different element. That would change it from nitrogen to carbon, for example, if we change the number of protons. If we change the number of neutrons, we're still working within the same element, but it gives us different isotopes of that element. So this would change the mass, but not change what element we're working with, and we call those isotopes. If we change the number of electrons an atom has, that gives us ions, different charges to that atom.